So dear colleagues and friends, a very warm welcome on behalf of NCRA. It is my pleasure to welcome you to this inaugural Govind Swarup Memorial Lecture. As we all know, we lost Govind Swarup last September, and with his passing, the world has lost a pioneer from the stage of astronomy and astrophysics. And India lost a true trailblazer who set up the foundations of a new branch of astronomy in the country, starting pretty much from scratch and leaving behind a tremendously rich legacy. In his honor, we have decided to start this annual Govind Swarup Memorial Lecture from this year onwards. And it will be timed to happen on or around his birthday, which is 23rd March today. And I'm very pleased that we could make the inaugural lecture happen exactly on the date of his birthday. Our aim is to have a lecture by a prominent personality who has made outstanding contributions to radio astronomy, be it in instrumentation for radio astronomy or setting up of new radio astronomy facilities or experiments, or in research work in this field. When thinking about who would be an ideal person to deliver this inaugural Govind Swarup Memorial Lecture, our unanimous choice at NCRA was to request Professor Ron Ekers to do the honors. And I'm very pleased and also extremely grateful to Ron that he agreed readily, including making time in his busy schedule to ensure that this inaugural lecture can be delivered specifically on Govind Swarup's birthday. So thank you for that very much, Ron. Much as we would have appreciated to have this event with Ron present amongst us in person, current times prevent us from doing so. And hence, this is a completely online lecture. But from next year onwards, we hope to be able to be back to a more normal style. So though we will miss the warmth of a personal interaction of the audience with Ron, I'm sure that this will nevertheless be a truly memorial lecture. So with those words of introduction, I will hand it over to my colleague, Jairam Chengulur, to introduce Ron and get the proceedings going for today's lecture.
Yeah, thank you, Yashwant. It's a pleasure to introduce Professor Ron Ekers. Professor Ekers obtained his PhD from the Australia National University, working with one of the pioneers of radio astronomy, John Bolton. His professional career has taken him to leading institutions across the world, including Caltech, the Institute of Astronomy, Cambridge, and the University of Groningen in the Netherlands. He was the director of the US NRAO's Very Large Array from 1980 till 1987, following which he was the founding director of the Australia Telescope National Facility. From 2003 to 2006, he was the president of the International Astronomical Union. He has long been a major proponent for international cooperation in radio astronomy and was the chair of the SKA steering committee from 2000 to 2002. His numerous honors and awards include the Federation Fellowship, the Grote Reber Medal, the Matthew Flinders Medal. He is a fellow of the Australian Academy of Science, the Royal Dutch Academy of Science, the Royal Society of UK, as well as the US National Academy of Sciences. Professor Ekers has long been a champion for innovation-driven radio astronomy, the topic of today's lecture. And for example, he was one of the early proponents for the use of phased array feeds in radio astronomy. He's also specialized in innovative applications of radio astronomy techniques, including, for example, obtaining wide field of view images using interferometers, a technique called mosaicing, which is widely used today, as well as using the moon as a detector for extremely high energy particles. His early contributions include the first measurements of the gravitational deflection of radio waves, as well as the first measurement of the velocity of the solar wind. We are particularly pleased to have Professor Ekers deliver this inaugural Govind Swarup lecture. Professor Swarup himself began his radio astronomy training in Australia, where, among others, he worked for a while with John Bolton, the same person with whom Ron Ekers later did his PhD. Professor Swarup was also a great proponent of international cooperation in radio astronomy. He was one of the early proponents for a large international radio telescope with a collecting area of the order of a square kilometer. And as long back as 1993, he, along with Professor Ekers, had proposed setting up an ERSI global working group to take up this challenge. So it's hard to think of somebody who'd be more appropriate than Professor Ekers as the inaugural lecturer. And as Yashwant said, we are particularly pleased that he's accepted our invitation to do so. So with that, I hand it over to you, Ron.
Okay, if you unshare your screen, I can take control.
I'll do that in a moment. Yeah.
Okay.
Yeah,
so
now.
Thank you, Jairam, for that introduction, reminding me of some things which I'd almost forgotten about. And thank you, Yashwant, for organizing this. So I hope you can see a blue screen, which is my beginning.
Yes, that's correct. And it's in presenter mode, so we are all set.
Okay, so let me go from there. Well, obviously, it is an enormous privilege for me to be able to give this inaugural lecture to my, my dear friend, Govind, who I interacted with over many years. And we always found that we could talk about new ways to do things so freely. It was always a great pleasure, and I always enjoyed occasions when I could visit. And perhaps as I go through this talk, I might relate some of those. Now, Govind was born in 1929, and it struck me that there was an interesting similarity between Govind's career and the entire existence of the field of radio astronomy, which started just a few years after he was born. And I've just given some highlights in this very crude overview slide of this entirely new field of radio astronomy, which started with Jansky in 1933. I will revisit some of the 37, Jodelbank, Parkes, the Netherlands. I just picked some charismatic telescopes, the VLA, the GMRT, of course, and then International Project ALMA. And I also realized when I did it that radio astronomy almost instantly became very international. And another thing that is striking is we have always had the greatest camaraderie and companionship between everybody in the world. And certainly something that Govind always enjoyed. So as I just said, Govind's life is actually contemporaneous just about exactly with the existence of the new field of radio astronomy. And so that forms one of my themes as I go through some highlights that have occurred in the history of radio astronomy. I will connect them with Govind, and in fact, I found it really easy to do so because he has touched so many things and been involved in so many aspects of radio astronomy. So as Yashwant already told you, this would have been Govind's 92nd birthday, days right, on the 23rd of March, 1929. And in 1929, Jansky was building the telescope. You see, do you see my cursor, by the way? Can I use the cursor? I'm
yes, we can. Yeah, we can.
So that might be useful as we go on. So this telescope was being built as Govind was being born. Now, I doubt that Govind would have realized that quite then, but pretty soon he was to become heavily involved in this field that started as he was born. Well, the remarkable thing about Jansky's telescope, which was set up to look for sources of interference on the new transatlantic communication as a commercial enterprise by by Bell Labs, he discovered not only some of the sources of interference, the lightning, for example, but he found a signal which, unlike any other signals, was peaking 4 minutes earlier each day. And even though he was an engineer, he realized that that was keeping track of star time, not Earth time, not the solar time. And so he immediately recognized that that signal had to be coming from outside of the Sun-Earth system. This was completely unexpected. Not only was it unexpected, it was not even explained for another 25 years exactly where the signal in the Milky Way was originating. And I'll get to that story as I work through this. Now, I thought it would be really nice if I could find a picture of Govind when all this was starting up. And thanks to Bina and Aju, they've come up with this incredible family gathering of Govind's family. So here's Govind. And this must have been some huge event. Bina thinks she recognizes some of his cousins and some of his family. Interestingly, it's the first time I saw a picture of Govind without his cheeky, wonderful smile. So I think he might have been a little bit intimidated by the family that was surrounding him. So he's about 10 in this photo. And at that time, Grote Reber was building his dish. Now I will return to Grote Reber in a minute, but I just wanted to compare this with my last discussion with Govind, which was on his 90th birthday. And in a corner on the couch, as you can see, the 4 recipients of the Grote Reber Medal had collected. And as usual, Govind is completely dominating the discussion as he explains to us his new ideas of what he thought would be a great thing to do in the future. So this was Govind at 90 and as enthusiastic and as visionary as always. So that introduces Grote Reber. And one of the reasons, of course, there is a Grote Reber medal. It is for those of us who have tried to make innovative contributions in the field of radio astronomy. And the Grote Reber was incredibly innovative. In 1937, that is when Govind was about 10, Grote was building a parabolic dish in his backyard. The first time, this was after Jansky. This was the first experiment to look for these radio signals, which were coming from the Milky Way. And Jansky decided that a parabolic dish with a focus would be a way to do it. And that was partly because he wanted to be frequency flexible. He didn't want to build an array like everybody else was using that would work only at one frequency. He thought it would be better to explore with a parabolic dish, much like a parabolic optical telescope, which focuses the radiation at one point at the focus. Everybody assumed that the radiation Jansky had seen would have been thermal radio emission from hot gas between the stars. And so on that basis, Grote Reber started looking at high frequencies because the thermal radiation would have been stronger. But he didn't see it at 3 gigahertz. He didn't see it at 900 megahertz. And it was only when he got down towards Jansky's frequency that he finally detected the signal. So right away, he had found the signal was stronger at longer wavelengths. And that was completely opposite to the predictions. It could not be easily explained as thermal emission. And it was in fact another decade before the idea of synchrotron radiation emerged. And it was realized that this was high energy particles radiating in magnetic fields. And thus, through radio astronomy, we suddenly had a link between cosmic rays, magnetic fields, and the region between the stars in the galaxy. quite an incredible change in the network, the connections between the different branches of the science. So I will come back to this parabolic dish later, but now I will introduce my second theme. And what had always struck me about Govind was his incredible innovative ideas. And so I thought a good way to celebrate that on this, in this lecture would be to talk about how innovation has had such a huge impact in the science of radio astronomy. So we've seen two examples of new instruments, and you will have noticed that neither of those were driven by any scientific theory. And in fact, their observations couldn't even be explained by the best theories at that time. In Howitt's book, Cosmic Discoveries, he makes an analysis and shows that in astronomy, most discoveries have arisen from technological innovation. So this widespread belief that pure science comes first and instruments are built or used to test theories doesn't fit this pattern at all. What's even more surprising is this notion that you do pure science and you then observe predictions to test theories is the basis for most funding for grants and for observing proposals. And yet, as I will show in my talk, there is very little evidence that this is the right model. Instead, we have something which is called technoscience, a term which has been introduced for other fields of science, where it was realized that it was instrumentation driving the science and not the other way around. And Woody Sullivan, in his wonderful book on cosmic noise, has quite a few pages talking about technoscience. Where are we? Okay, and there's Woody's book, which I can certainly recommend to you. The term technoscience was introduced to explain how instrumental developments have driven scientific understanding. And radio astronomy is a classic case of a technoscience. And Govind's career illustrates that with in many, many cases, as I will go through in this talk. A term was introduced actually in 1930. That is, the people who did technoscience were technoscientists. And it's almost as if the word was needed because Govind had been born, and that was the description. A couple of pictures here showing Govind at work in various places, building instrumentation, which of course he was wonderful at doing. Now, I'm not giving an autobiography, but I'm touching on Govind's career as it is connected to different instrumental things which I wanted to talk about. And so I will just jump along, and I will leave it to your research or to others in future to fill in all of the biographical details. But Govind, after he'd got his degree, finished up having a period of study in Australia and organized by Pawsey. He worked with three of the leading radio astronomers in the CSIRO group in Australia. One was Christensen, then also Mills, famous for the Mills Cross, and Paul Wild, famous for the solar heliograph. So I'm just going to illustrate one aspect of his work in Australia because it has many repercussions. He was working with Chris Christensen. This is Chris Christensen here. And in order to make observations of the solar emission from the sun, Chris had built this thing called a crisscross, which is an array of a large array of dishes, one in the north-south direction, one in the east-west direction. They're on the edge of the Potts Hill Reservoir, and it's named after Potts Hill. And so Chris was given the job of, Govind was given the job of working on this with Chris. Now, the idea of this telescope was that each each of the array of dishes could make what's called a fan beam. That's a very long, thin beam. And they were observing the sun, and that would give you a strip of emission across the sun. And then you could make different fan beams pointing in slightly different directions by changing the phase gradient along that row of dishes. And that would give you what's called a strip distribution. Then as the Earth rotates, you get another one at a different angle. And so the problem is, how do you combine all of these, what we call strip distributions, into an image? What Christensen had realized was that the crystallographers had actually solved an identical problem by using Fourier transforms. Now, I'm not going to talk much more about Fourier transforms, so don't worry if you are not into the wonderful mathematical world of the Fourier transform, but it is a mathematical process which enables you to, for example, combine these multiple strip distributions into an image. So Govind Swarup had just arrived from India, and so one needed some work for a young student to do. And so he was given the job of hand calculating the one-dimensional Fourier transforms for each strip. And then when he did the Fourier transform, he would plot those Fourier values on some two-dimensional graph paper, and then do it again at another angle, which gives you another line, until eventually you fill in the whole two-dimensional paper, and then you do one big two-dimensional Fourier transform, and you get an image. So to do this Fourier transform, Govind used an electric calculator. Govind has told me in a discussion that it took him 1 month of solid calculations to make the following image of the sun. So there it is on the left. And in fact, it is quite a famous image because that is the first computed two-dimensional aperture synthesis ever made. This precedes, as I will mention in a minute, the work that Ryle was doing in Cambridge. However, in Australia, this was not used anymore after this initial two-dimensional image, because it had taken many months with this calculator, a very hardworking Indian student, and the people like Mills had decided it was completely impractical as a tool in radio astronomy. So they went back to build things like Mills crosses, which form instantaneous beams, and they do all their Fourier transforms in analog. However, as we will see as I go through this talk, this calculation set Govind thinking, and I'll tell you about the idea he had, and this is based on what he's told me. I don't know if it's written down anywhere. The thought that came to him while he was doing all these calculations. This telescope from Potts Hill, as a combination of Govind's suggestion and strongly supported by Joe Pawsey, when they finished the observations in Australia, it was shipped to India, where it became the Kalyan Array. And with Govind's help, it was brought into operation in India and was the first major Indian radio astronomy facility. And Govind, I think, might be one of the ones sitting there on the left, getting it working. But then a year later, Govind had gone back to India, but then a year later, he decided to go to the US to continue his career. In the meantime, he had met the wonderful Bina, his wife, and there they are traveling through Texas, and the wonderful, charismatic Govind in all of these images. Spent some time in Texas, and then he finished up with Ron Bracewell. This is Ron Bracewell here, who had built a copy, basically, of Christensen's telescope in Stanford to do further imaging of the sun. This picture is a bit interesting because they're at the site of this telescope, and this fellow sitting here on the chair is Pawsey. And what Pawsey is doing just off screen to the right is chiseling his name on the pier of one of the Bracewell telescopes. And this is one of the famous set of piers that is now erected at the DLA by Woody Sullivan as a sundial. And all the names have been recovered by Miller Goss. So here's the array that Bracewell had built at Stanford, and the one in which Govind was working and did his PhD. So I will mention two innovations that came out of his period in Stanford, in addition to the well-known fact that he did a PhD on aperture synthesis imaging. One problem you have with these telescopes is the time has to be kept precisely between all of these different elements. So when a radio wave arrives out in space, you can combine the signals from one this end and one this end, and you can do it lining up the voltages in the radio wave to an accuracy which has to be better than microseconds. So that is technically very difficult. And Govind invented what's called the round-trip phase correction method to solve that problem. And what you do is you send a signal out from the center, for example, out to one end, and it bounces around and comes back again. It's easy to measure the time difference here because you've got the two signals close together. Then you say half of that is the time difference going out along the cable. And in that way, he did the correction for the phase. And this round-trip phase correction has been used in probably almost every radio telescope interferometer that has been built since then. So a wonderful example of just a truly innovative idea that Govind came up with. The other thing that happened, again, based now on the stories which Govind has told me, he said he was thinking about this terrible calculation he was doing to convert the strip scans to two-dimensional images. And in thinking about it, he realized that instead of transforming everything with the 1D Fourier transform and then transforming back with a 2D transform, if you applied the right convolution to the strip scan as the first step, then you could just add the strip scans together and they would make a two-dimensional image. And he says he remembers discussing this, what's called the back projection algorithm. Back projection because these scans are like you've projected an observation, that's something that's two-dimensional into a one-dimensional space, and back projection is coming back from one-dimensional to recover the two-dimensional object. He talked to it about Bracewell. Now, Govind himself didn't pursue this any further, and Govind said to his surprise, in 1967, Bracewell and Riddle published what became a very famous paper on the back projection algorithm. Now, between them, they had actually worked out this deconvolution procedure. And while it was never used in any major way in radio astronomy, this had a huge impact on medical imaging. Over on the right, you see two pictures of an X-ray image. Now, when you take an X-ray image, you have done a projection of everything that's inside of your three-dimensional object into a two-dimensional space. And then what you do in an X-ray imaging system, a CT scanning system, is you make those images with many different angles, and then you combine them into an image. But in medical imaging, these images were so big, there was no possible way of using either calculators or computers back in 1967. And so they needed an analog way of doing it. And it turned out the back projection algorithm was exactly what was needed to remove what's called the shadowing in medical imaging. And there's a whole string of medical imaging papers from that period showing how this algorithm could greatly enhance medical imaging. So, Govind's ideas paid off in completely unexpected ways. And I will continue on this theme for a little bit. At the same time that the Australians, Pawsey, Christensen, were doing their aperture synthesis observations in Australia, Martin Ryle was pursuing exactly the same idea with really very similar equipment, which was World War II radar equipment, and building also a system to do aperture synthesis imaging. The two were in contact, but were working fairly independently, but in a reasonably friendly way. There was no animosity between the two groups, but they were nevertheless competitive. However, Martin Ryle made a step which I think generated a huge separation between the two groups. The EDSAC-1 and then later EDSAC-2 electronic computers were being developed in the Cavendish laboratory in a building next to where they were working in the Cavendish. So naturally, people were thinking, instead of an electronic calculator and Lipson-Beaver strips to do Fourier transforms, maybe it could be implemented in an electronic calculator. And with the help of the crystallographers, that was exactly what happened. And Blythe was actually the first to do 360 1D transforms, same kind of job that Govind was doing in many months. And it took him 15 hours to do it on an electronic computer. I found it curious that his output from this program was not a bunch of numbers, because an image of the sky in numbers, what could you do with it? There's no plotting machines, there's no way to do that. So his output was actually the contour maps themselves and not a digital image, because there was no such concept then. It's just a side note, which I think was in here for another reason. Many of you will have read Bracewell's famous Fourier transform book, and that is based on a small book that Roger Jennison had written using Radcliffe's lecture notes, which give the explanation of all this stuff that was going on in Cambridge. Let me skip that. The application, which was absolutely dramatic, was this image of the North Pole made by Ryle and Neville. They were using the 4C antennas, and this then, and because the North Pole, you only had to point in one direction, they were able to use the 4C aerials to do a synthesis image. And so this is the first Cambridge Earth rotation synthesis image. And it was a spectacular advance over anything which had been done before. It is also computed on the EDSAC electronic computer, and I've been lucky to be able to find, with the help of Malcolm Longair, this wonderful picture of Anne Neville from Neville and Ryle feeding the paper tape into the EDSAC-2 computer in order to make this image. And Neville was later to become Anne Gower and continued to do radio astronomy. Now, to go back to my first comments, this is 7 years after the image I showed you that Christensen and Govind had made. So Cambridge was certainly not the inventors of aperture synthesis, nor the first to use it, but their use of the electronic computer was what caused the revolution and which made aperture synthesis completely practical. And an Indian with a calculator could not compete with an electronic computer. So that's my story of aperture synthesis. So let's go back to the single dish story now for a while. So here's the dish which Grote Reber built. It's built in his mother in the backyard of the house where he lived. Apparently, the clothesline that was used by his mother to put the washing out used to be there. And so when Woody Sullivan was trying to find out why Grote Reber never observed on Mondays, it was because she was using his dish as a clothesline. So that parabolic dish then became the inspiration for many more dishes. Jodrell Bank, which I showed you in the first slide, then a few years later, Parkes. Now, I put the Parkes dish here because I want to introduce another small story which relates to Parkes. And this is partly because with Milagos and Claire Hooker, I'm currently involved in the detailed history of the development of radio astronomy in Australia. And I was curious as to why did the Australians build this big dish? Was it because there was an astronomical problem that needed a big dish to solve it? Well, that is true to an extent, but it was not the major reason. The major reason was the UK were building the Lovell telescope, and Britain and Australia were the two top countries doing radio astronomy. And so it was argued that if Australia didn't have a dish like the one that was being built at Jodrell Bank, then Australia would no longer have its role as being a leading radio astronomy country. And so the argument was based primarily on prestige. It's also interesting reading these documents. An argument on prestige is what funding agencies actually pay attention to. Whether or not this was going to be good for looking for faint signals from neutral hydrogen was certainly listed, but it wasn't the reason why it was built. The other thing which is very interesting about Parkes is that more than half of the funding came from the US, and it came from granting organizations, foundations in the US who were funding science globally. And the term at the time was, this was science diplomacy. When you want to build good relations with people in the rest of the world, a wonderful way to do it is to help in things like this with the science. There were no strings attached. There was no agreement on Americans getting time on the telescope. It was done because it was a great project. And the innovative technology that has been used since is one reason why it is still a world-class telescope. More of that in a minute. So there were more big dishes built. Here's the 100-meter dish in Bonn. And here's another big dish. This is the 45-meter dish, which is part of the GMRT array. You noticed it looks very thin and transparent compared with the dishes I just showed you. And that's because this dish was built at least 10 and probably 20 or 30 times cheaper per square meter than the previous dishes. And that meant you could make a big array with big dishes in it. And of course, that was going to be Govind's idea and the inspiration for the GMRT, which we will get to in a minute. Govind's trick for doing this is what he called the Indian rope trick. And I remember being totally impressed as he gave this talk. The method of construction is a bit like an umbrella, which is upside down, and you have ropes, or steel wires, of course, which are in tension, which form the shape of the dish by pulling against the steel frame. And this is all set out in great detail. So this way, you could build a relatively large dish at very low cost. Again, I will get back to this later because I want to do a little side excursion because this influences something Govind did in the next piece of my talk. So that Parkes Radio Telescope, its great advantage was its flexibility. And it was able to do many things which were not seriously considered as part of the motivation. And one of the flexibilities is with a big dish, you can point it anywhere at any time. So if a radio source is going to go behind the moon and you want to observe what happens as it disappears behind the moon, as we can see in the diagram here, then you've got to point at a certain place in the sky at a certain time. And the big dish gave you the flexibility to do this. So here's the signal of this radio source, number 273 in the third Cambridge catalogue. First of all, showing some Fresnel diffraction patterns and then disappearing behind the moon. And then we wait a little bit longer, comes out the other side, another Fresnel diffraction pattern, and it reappears. And there's even some little features like this little bump here, which are real. And those features enabled Cyril Hazard to put together a crude picture of this radio source, which had a point there and a jet coming down to a region down here. This was done to now great precision, much better than a second of arc. And so they could lay that on the top of a photograph, and the point source was what they thought had been a star, and the piece coming down here is what we now call the jet coming out from this source. Martin Schmidt was notified about this because Martin was the person using the 200-inch in the US to look at faint galaxies, which were being found identified with radio sources. And as soon as he took the spectrum, he realized that it was very unusual. This was not a star in our galaxy, but this was a spectrum that had a huge redshift. And that meant this object was brighter than a galaxy, much brighter. It also meant that it would be visible to great distances in the universe. And so if you look back through the records, this is the real beginning of observational cosmology. Now it became clear that both radio and optical sources could be seen at redshifts where the cosmological effects of the curvature and the formation of the universe are having a huge effect. Not only was observational cosmology born, but a few weeks later at a meeting of gravitational collapse and relativistic astrophysics, which was a rather esoteric meeting up until Texas 1963, where relativistic general relativists would meet and talk about their usually inaccessible theories. All of a sudden, here was an observation for which their theories were required, because the energy which had to come from a very small region could only be provided by something like a black hole. So this was the beginning of black hole astrophysics, AGN astrophysics, all from this observation. Now, Govind had gone back at the invitation of Homi Bhabha to form a radio astronomy group in India. This is after he's finished his PhD in Stanford. And Govind has been hugely impressed by this observation of an occultation of 3C273. So he says, how can we build a telescope in India which could do things like this? And he came up with this incredibly innovative idea of a cylindrical parabola on the side of a hill, so its axis was parallel to the Earth's axis. And so with the huge collecting area of this cylindrical paraboloid, he could track sources across the sky. And his scientific driver for doing this, so he could do occultations and he could do it on faint sources. It has been a very successful telescope, has been used for many things, including occultations, probably at the moment, most importantly, for studying the solar wind through interplanetary scintillation. A wonderful legacy and a telescope which is still functioning. At about this time, the US had, of course, seriously joined the game of radio astronomy and with adequate resources to build another big array, and that is the famous VLA in New Mexico. Now, I'm not going to go into any detail talking about how the VLA was built and all the other wonderful things, but I will make two comments because they fit into the rest of my talk. The prime goal for the VLA, very clearly laid out by Dave Heshan, was to be able to make radio images with optical resolutions. Dave insisted that there be one very simple scientific reason for building the telescope, which would be easily understood by people who fund large things like telescope. So when you read the proposal for the VLA, it is very clear that while there is, of course, a strong science case made, right up front is to make radio images with optical resolution. I picked one image. I picked it for two reasons. Govind loved to show this picture. I'm not sure why, but clearly it triggered his imagination. It is in the reddish pink color, the radio image from the VLA of a radio source, the strongest in the constellation of Hercules, so-called Hercules A, and it's superimposed on a very nice optical image of the field. And we have a galaxy here, which clearly has an AGN and a black hole in the nucleus, ejecting these jets of emission, which are making these wonderful smoke rings as they go out into the lobes of the radio galaxy. Can I remind you that when the VLA was proposed, no jets had yet been found. So this, of course, was not itself part of the science case. But the idea that when you imaged a radio source at optical resolution and you would find really exciting things paid off handsomely. Well, Govind wanted to play the same game in India, and so his visions then grew bigger than the Ooty Radio Telescope. And in 1982, he said, let's build an array using these smart design dishes. They can be big, 45 meters in diameter, and we will have lots of them. And that is the origin of the Giant Meterwave Radio Telescope, which has not only been functioning since 2000, but a couple of years ago, and I was delighted to be invited to the opening ceremony of the upgrade, and it is now one of the top telescopes in the world. Govind was involved in the opening ceremony, which was just before his 90th birthday, and I'm sure he was genuinely proud, but he was talking about, but what do we do next? That was Govind. And beautiful picture of the GMRT. I have had to skip over the many discoveries being made in radio astronomy. And so just to give you a tiny vignette of everything that's going on, I pulled out this old slide I had, which are the 4 Nobel Prizes, which are in radio astronomy. And 4 Nobel Prizes in the period in which the science has existed is actually quite spectacular. There was the discovery of the microwave background radiation by Penzias and Wilson. While there had been a prediction that the microwave background would have existed, their observations were completely independent of that. And it was some time before they realized that they had in fact discovered the background radiation. Then 20 years later, the properties of that background radiation, which is coming from the early universe and is the time when the first structure is forming. And so both the spectrum of that background radiation and the anisotropy are hugely important questions for the understanding of the evolution of the universe. And a Nobel Prize was given to John Mather for measuring the spectrum and George Smoot for detecting the anisotropy in the background radiation. Shortly after the CMB itself was discovered, we have the discovery of pulsars and the Nobel Prize for that given to Tony Hewish. But as most of you know, the actual discovery itself was made by Jocelyn Bell using this telescope, which of course had not been designed to detect rotating neutron stars. There was no concept by any radio astronomers that such a thing would exist, but it was to study interplanetary scintillation, the same phenomena which I just mentioned that Ooty is currently continuing to observe. And the Nobel Prize was shared with Martin Ryle for aperture synthesis. And if you read the citation carefully, I think it is deserved and well written, even though earlier I did point out that aperture synthesis had been discovered in Australia, published in Australia. But Martin Ryle did two things which were hugely important. He made it practical by integrating the computer into the aperture synthesis, and then realized that he could go on to use the technique to observe the faint extragalactic radio sources. And so, as the citation says, it was not just for the invention, but the application of aperture synthesis for which that Nobel Prize was given. And then yet another Nobel Prize to Joe Taylor and his student Holtz, when they showed that pulsar signals were changing in the way predicted if that binary system had gravitational radiation. I'll use that pulsar observation just to pick up one other example of innovation before I get into the concluding section of my talk. And here is an example of an innovative receiver, which is going on to the Parkes telescope. And it's innovative because instead of one beam, there are 13 beams, all with very low system temperature. So the telescope is going to be able to look in 13 directions at the same time. The receiver worked very well, and it was heavily involved in surveys of neutral hydrogen, which was the reason why it was built. But it was quickly realized that it would make an incredibly good instrument for surveying pulsars because it could do it 13 times faster. There's a picture of the actual receiver, which, by the way, while it's there to remind me that the engineering behind these innovations is in itself a beautiful and artistic process of building something which works as well, but is also beautiful. Unfortunately, all put in a steel case, so you don't see it afterwards. I was listening to a talk by Andrew Lyne, and he showed the image over there on the right. I hope it's not cut off by the, my version is, I can't do anything about it. My version is a little bit cut off by the images on the right of my screen. But
no, we see it. We can see it.
You can see it, okay. This is the, look at the image on the right for the moment. And as I said, this was from a talk which Andrew Lyne had given. And he was showing the rate of discovery of pulsars going back to 1970 and continuing on, and comparing the rest of the world in red with just the ones discovered at Parkes, which is doing as well, and perhaps was doing slightly better, but quite comparable to the rest of the world. Then a new receiver was built, actually built for looking for H1 in extragalactic, in galaxies. And that occurred at this point in time. And so we have this huge spike, which is due to the use of a new receiver. It made me realize that instead of counting for citations for people who write clever papers, or even for observatories, we should have a citation measure for receivers. And here is the impact of that one receiver and the citations to publications done with that receiver, which would look pretty impressive in anyone's record. So I hope one day, in the spirit of the importance of instruments and instrumental innovation, that we might actually use things like citations for more than evaluating which scientists can write better papers. Now I want, let me see, I think I have about another 5 minutes, Yashwant, or something like that.
Yes, I think that's fine, Ron.
Okay. Here I'm going to give an example, which is innovation, which did not impact radio astronomy, but had perhaps the biggest impact of any radio astronomy innovation has ever had in the world. And this is going to be the discovery of Wi-Fi. And the story, which is known to some of you, but many people don't know the backstory to how John O'Sullivan came to, and his group came to invent and patent the 802.11 system, which is what all Wi-Fi systems use. So while I was in Cambridge, I was able to interact with Stephen Hawking, who was already showing the first signs of his disease, but was still, you could easily discuss. And at the time, he was coming up with his theorem that a black hole would actually radiate like a black body. If a black hole wasn't very large, the time scale for it to lose all of its mass by radiation was actually less than the age of the universe. And the lower the mass is, the faster it would go. So you get an exponential explosion as this black hole finally disappears. Then Martin Rees, who was also at Cambridge at the time, realized that in that explosion of a black hole, there would be an expanding superconducting shell of high energy particles. And this would make a pulse of radio emission. And so maybe somebody should look for it. Well, I was in the Netherlands. John O'Sullivan had come from Australia to the Netherlands, and we were also working with Peter Shaver. So we decided, hey, maybe we should look for these exploding black holes. Now, the catch was the predicted pulses lasted for 1 RF cycle. So at a gigahertz, this means they would only last for a nanosecond. We knew they would be smeared out in the interstellar medium, so we would have to look for something maybe as short as a microsecond. So we went to John O'Sullivan, who was either then or later became head of the engineering group, and said, our normal time constants in radio astronomy are a few seconds, 10 seconds. How can we build a backend which will work with a microsecond time constant? And so John very quickly put that together. We also, we put that system that he built on the Dwingler telescope, actually, searched for exploding black holes, didn't find any, wrote a little paper saying, oh, too bad, wasn't there, let's go on and do something else. But in order to do those observations and to analyze that data, we had been recording the output on film, because when you're taking data with a microsecond resolution, and it's only 1970, you can't write it to a computer, that's impossibly fast. So we were writing on film with a special film writing system. And that generated reels of film, and we had to scan through the film looking for a dispersed pulse because we were writing time versus frequency. And so we had piles and piles of film, and it was a very boring process looking through all the film. And John O'Sullivan at that point said, this is ridiculous. There's got to be a better way. And he took 2 steps, which were crucial. First of all, he said, I could build a chip which could do a Fourier transform. Then we can put the chip into the telescope and we can search for this dispersed pattern in real time. But then we have the problem of all of the multi-path effects. But John O'Sullivan also wrote a little telescope with Johan Hammaker and Jan Noordam about how Westerbork, using its redundant spacings, was able to correct for the tropospheric delays the multipathing coming through the atmosphere. So he had two concepts sitting in his head. One was you could build a chip that could make a Fourier transform. And two, if you have redundancy, you can remove the multipath problem. The reason why Wi-Fi was a difficult problem to solve, and this is the way computers in a house can talk to each other, talk to their to the modems and the other bits and pieces, despite the fact that signals are bouncing off the walls and there's a lot of multipath going on. So he built a chip which could do the Fourier transform, use the Fourier transform to and the redundancy in order to, in frequency in this case, in order to correct for the multipathing. And on the basis of that, they patented a device which became the IEEE 802.11 and the basis for Wi-Fi. Here's just a picture of John O'Sullivan, and he's been given the European Inventor of the Year Award 2012. So here is something which started in basic science, didn't actually prove any theory about evaporating black holes, but it triggered a whole set of innovations which have had made a difference to the world. So as I get towards the end, let's look about making a difference in the world and about Govind as the international science visionary and the way he has influenced the SKA. Govind's first attempt, I remember very clearly, was Grote, the Giant Equatorial Radio Telescope. He saw this not only as a possibility to build a big telescope, but he said it would be a way to get these countries on the equator to have a natural reason for working together and join together to do a big science project. Well, Govind succeeded at most of the things he did, but this one was too hard. But if you look back, you can see he was laying the foundations for what became the SKA already. By the time he had started building GMRT dishes, he realized that if he had even more, that is 1,000, he could do what Peter Wilkinson also came up with. He could see the H1 signal from galaxies at cosmological distances. And so Govind was immediately thinking, how could we build an array like this? And he's doing this independent of the discussions which were going on involving Peter Wilkinson and a number of us in CSIRO at the same time. From those discussions in CSIRO, the concept of building a next generation telescope with a collecting area of about a square kilometer would be a wonderful project. And many people were coming up with interest and ideas from all over the world to do this. But the next step was actually taken in 1991, and Jairam mentioned this briefly. I was at a, I've jumped. In 1991, Govind made a proposal which he called the International Radio Astronomy Telescope, a published proposal with 160 75-meter dishes, centrally concentrated baselines to 200 kilometers. If any of you are aware of SKA Mid, there's a pretty reasonable description of it, and that was in 91. Now, in 1993, I happened to be invited to a European Space Agency symposium, which was actually talking about the future of things in space. But I wiggled in a talk on how there could be a future on the ground with telescopes such as an SKA. Govind was in the audience, and Govind grabbed me immediately afterwards, and I already knew that Govind had similar ideas. And Govind said, "Stop talking about it, Ron. Why don't we do something instead of all of this talk?" And Govind said, "Look, you're involved in ERSI. I happen to be the chairman of Commission J at that time. Why don't you set up a telescope working group within ERSI and actually make something happen?" And that was actually the beginning of the proposal to set up the ERSI Large Telescope Working Group. It was formed in the General Assembly in Kyoto, and Robert Brown, I think, was the first chair. And I think formally that international recognition was the formal beginning of the SKA project. On the way to SKA, and I'll flash through these, there have been precursors. That is, instead of building the entire SKA at once, how about building a precursor? And here's the famous Meerkat antenna in South Africa, the site chosen for SKA Mid. This is their fabulous image of the galactic center. And you make an image which has got this much detail and this much resolution. Look at all these little fine filaments. We knew about all the bright stuff. That wasn't new. But the incredibly rich and still not explained filamentary structure came out of that image. Another precursor was the array of telescopes, each of which have a focal plane array. Turned out that was fabulous for detecting these things called fast radio bursts. But with a wonderful piece of innovation generated by Keith Bannister, we can generate a trigger which dumps the voltages from all antennas so that in a millisecond, we can get the coherence needed to localize an FRB. And I think we're up to 17 localized FRBs now, and they are at great distance. And of course, because of that, and because they are a short signal in time, they're measuring the density of the universe. I will finish on another, what started as an SKA precursor. In one of the early meetings, the Chinese came with the proposal to build a big Arecibo, but a bit different from Arecibo, bigger than Arecibo, but an Arecibo with a deformable subreflector, so it could become parabolic in sections and generate a focus. Well, they have built this incredible thing, and in a combination of two bits of innovation, they have taken a big copy of the Parkes multi-beam receiver. This one's got 19 beams. It's a tiny dot in this picture, and they have the largest collecting area in the world, and it's observing with 19 simultaneous beams. And so just wait for the results as they start coming out from this wonderful machine. So let me sum up. I hope I have been able to convince you that the field of radio astronomy has clearly been driven by instrumental innovation. Sure, there's been other aspects, but instrumental innovation has been completely dominant. And of all the people in the world who have most been a driver of this enthusiasm, it is Govind. And he had this wonderful skill of combining a scientific pursuit with an innovative instrumental opportunity. He could see how to combine some possibility that nobody else had thought of with a real scientific problem to be solved. That was what he was brilliant at. Govind was a dreamer and a visionary, but the other spectacular thing about Govind is he made the dreams happen. So, from all of us, thank you, Govind.
Thank you very much, Ron. That was a fascinating walk through both Govind's life, and the history of innovation in radio astronomy, which I, and I'm sure all of us thoroughly enjoyed. So Ron's been kind enough to say that he could take a few questions. So if you would like to ask Ron a question, please do raise your hand if you're on the Zoom call. And if you're on the YouTube, please, type in your question and somebody will take it up. So the first question is from Herbjan van Langevelde. He's asked whether, the search with Westerbork for exploding black holes, would it have turned up a few FRBs? or was the sensitivity not adequate, or the search through dispersion space? Ron?
Yes, and let me just say there is a related question. Could FRBs be exploding black holes? Because of all the theories, that isn't one that's discussed. The answer is no. The mass of an evaporating black hole in Hubble time is such that the energy output is much too low to power an FRB at a cosmological distance. I also had a bit of a thought about whether we might have been able to detect an FRB. We didn't really have the sensitivity, although of course a super strong one, it could have happened. We looked in our galaxy at places like globular clusters. We also looked, I think, at Andromeda, but the amount of sky we looked at was far too small. But it could have happened, yes.
Yeah. Thank you, Ron. I think we have a question now from Shantanu Desai. Yeah, please go ahead.
Yeah, so thank you. Very nice talk. So I'll just ask two quick questions. So first question, I think you mentioned that someone else also had came up with the idea of aperture synthesis before Martin Ryle. So and could you just provide more details of that work, and also why it was not taken, why it was not that well known? Second question is, I think Joe Silk has been pushing for a radio telescope on the far side of the moon to detect for cosmological effects like non-Gaussianities from inflation and all. So how feasible is that maybe in the next decade? That's all. Thank you.
Okay, thank you. Two good questions. I will do them in turn. The first question was related to my rather cursory comments on aperture synthesis. The first publication of the principle of aperture synthesis is in a paper by Pawsey, Ruby Payne Scott, and McLean. They had made observations with what's called the Cliff interferometer of the emission from the sun, and had used the phase of the Cliff interferometer to identify that the emission was coming from the sunspots. This is in 1947. Then in that paper, they have about a half a page in which they say, if we measured, this is measured one Fourier component, if we measured many different Fourier components and combined them, we could even make an image of where the radio emission is coming from. However, the cliff has only got one height, and it's not practical to find cliffs with different heights. They also pointed out that they could do what's now called multi-frequency synthesis. They said, but we could change the frequency and that would get other Fourier components, but the sunspots have got frequency structure, so that won't work either. So there was the statement of the aperture synthesis, and that is years before there's even the first record in which Woody has researched in Martin Ryle's diary. In Martin's early papers, he includes a reference to this paper, but it disappears after about 5 years and isn't referenced anymore. So you ask why it isn't, well, and the reason, I gave the reason why it wasn't continued in Australia, and that was basically because without the electronic computer, the Fourier transforms do not make it a very practical method. So that was the big difference. The reason why the paper is not well known, I find is interesting, and it's a message for people today and when they're writing papers. Aperture synthesis was half a paragraph in a paper, a famous paper about the way that radio emission comes from sunspots. The paper is highly referenced by the solar community because it was the beginning of solar radio astronomy. But everybody overlooked the fact that aperture synthesis was in it as well. So it's not such a smart idea to throw every idea into a paper, and the paper was titled Radio Emission from the Sun. It wasn't titled Aperture Synthesis. So it has a modest number of references, but it isn't very well known. By the way, my co-author on the book we're writing would also point out that there is a major Northern Hemisphere, Southern Hemisphere imbalance. Things done in the Southern Hemisphere, there's less people who cite it. And at the time all this happened, Australia was a mere colony of the UK and were treated as such. So, of course, the UK always got the credit. Okay, sorry. And your second question was?
On the far side of the moon.
Going to the far side of the moon. Well, this is great visionary stuff. Whether it will solve, which problem it solves, we don't know. But of course, the far side of the moon has got the great advantage of being free from any radio frequency interference, which is then blocked by the Earth. It is, in fact, the only place in the solar system where you can escape from radio frequency interference from the Earth. So I am a great advocate of trying to build a telescope on the far side of the moon. Good project.
Thank you. Are there any more questions? If you'd like to ask a question, please go ahead and raise hand. Yeah. Avidesh, please go ahead.
Hi, Ron. If there were to be one question on which you and Govind would have liked to sit together and think intensely about resolving, what would that be at the present time?
Oh, Dash, you always ask the difficult ones. Just at the moment, I have found the fast radio burst mystery quite fantastic. And so thinking of innovative ways to observe phenomena which happen so rapidly, I certainly could imagine talking to Govind about that. And I suspect there will be innovative ways to address this problem. It is interesting, of course, that the Canadians have built cylindrical paraboloids, just like Govind did. They're sitting in Canada, so they can't quite find a slope to put it on an axis which is parallel to the Earth's axis. So I can just see Govind smiling here, saying, you know, I had a much cleverer way. But that cylindrical paraboloid is a very cost-effective way to get a lot of collecting area, exactly the argument that Govind used when he built his dish. I didn't have time to mention everything in my talk, so I didn't mention it. But maybe we would have talked about clever ways to find FRBs, which are at cosmological distances.
Thanks.
Yeah, thanks, Ron. Are there any further questions? I'll just check with Yashwant. Yashwant, if there's anything on the YouTube, maybe you could sort of voice them, and I'll hand over to you at this point.
Yeah, thanks, Jairam. I could not see any questions on the YouTube, and I think we don't have any other questions from the Zoom panel also. And so I think we could actually come to a conclusion to the formal lecture and the question answers. And I just take the opportunity to thank Ron once more for an excellent talk and for agreeing at relatively short notice to take this up and provide us what I would call a great start to this lecture series, which I hope will become something that, as you know, has been admirably started by Ron, something that highlights technological innovations and the growth of radio astronomy. So thank you very much, Ron, and thank you everybody for joining us for this meeting. Thank you, and we will now close.